So it looks like we got to be done just before 12:30, so you can run down and grab lunch, right? Okay, so we'll try and keep this going on time. Welcome to Challenges and Opportunities of Gas Flow Measurement and Ventilator Testing. I'd like to introduce my colleague, Daniel Benz, and he can tell you a little bit about himself.
Hello, everyone. My name is Daniel Benz. I'm the managing director of the US entity of IMT.Analytics based in St. Petersburg, Florida. I'm originally from Switzerland, but have been living in Tampa now for 1.5 years. And the bad news for you guys about me being from Switzerland is you have to deal with my accent today. But the good news is I just came back from there and I brought some chocolate for you guys. So grab some. Yeah. Kerwin, maybe you can walk.
Yeah, I'll just continue. We'll just pass around. Everybody's cool.
Yeah, pass it around.
Pass it up and down the aisle. Help yourself.
A little more about me. I've been in the medical device industry for 12 years now. I'm an engineer by training. I held different roles in customer service, tech support, but also technical training for both ventilators and gas flow analyzers, means ventilator tests we are going to talk about today. So with that, I would like to hand it back to Kerwin to introduce himself a little bit and to start the session then.
Hi, I'm Kerwin Sanger. I've been with IMT.Analytics now for a little over 8 years, and I've been in the industry longer than I care to admit. I've worked for companies like IMT, of course, and before that, let's see. Started out with Puritan Bennett, Respironics that turned into Philips, Nihon Kohden. So I've been in a lot of different roles. I started out in engineering and I went into ventilator service training. So I spent a lot of time doing that for several companies. I've done depot repair management and things like that. And I'm currently the business development manager for IMT. I'm not Swiss. You probably can't tell from my accent, but I live just down the road in San Diego or near San Diego. So, all right. We're going to try and pace this, pretty fast. We're not going to get into a lot of detail on everything. We won't go into, specifics about models of ventilators or things like that. We want to talk in generalities. We want to talk about things that might help you overcome some challenges that you might face, and we want to talk about those opportunities. Okay, let's see if we can get this to work. That's us. Before we get started, can we kind of have a show of hands and show who's currently or normally works on ventilators or anesthesia machines? Good, so pretty good mix. How about people here that maybe have never worked on a ventilator anesthesia machine? Tony. Okay, so we've got a good mix here. So for those of you that have a lot of experience, if I say something that's a lie, you can call me out on it. For those of you that are new, if it's a little bit over your head, feel free to ask questions. Okay, we want this to be interactive. But we'll try and talk in terms that will help everybody. We want to make sure that we're giving you some basic knowledge so that you can, along with the technology that's out there for gas flow analyzers, be more successful in your testing, okay? Both Daniel and I now have been focused on the test equipment side for quite some time. And so the things that we want to share with you today are challenges that we've actually faced or heard of through tech support, in the classroom, in the repair depot, things like that. So we're not just making them up, they're things that we actually face. There's probably a lot more challenges out there. We only have time to maybe talk about 3 of them today, but we'll go through them and we'll try and build your knowledge base so that you can take that knowledge and look for your own opportunities to overcome challenges. Okay, questions? Let's jump right in. Our challenges that we're going to talk about today. The first one, complex and unclear measurement setups. Okay, you may be testing a wide range of devices out there, and there's all kinds of different setups. So we'll talk about those. Ensuring that your gas flow analyzer is set up correctly. There's a lot of settings on your analyzer. We're going to talk about some of those and help you with those. And we want to make sure that you're understanding the test sequence and the ranges that are defined by the manufacturers. We're going to see that sometimes those are pretty ambiguous. Okay. All right, first one. Let's talk about setups. You may or may not recognize these, but here's a couple of photos in my first example. This is directly from a service manual. It's 2 photos of 2 different setups using a flow analyzer to do testing on a ventilator. They did actually a pretty good job here because they took photos. They show you a bunch of connections. They show you the tubing connections, the cable connections. They show you the ventilator. They show you the analyzer, and they show you a test lung if there is one. But there's a few things that you might not quite be able to see here, like if you look closely, there's a pressure that's been teed into the analyzer here. Okay. If you look at this photo, you'll see that they've teed in an oxygen analyzer. So when you're doing your testing, you have to make sure that you have all the components that you need, and you need to understand your device so that you know how to apply it for all the tests that they're asking you to do. Here's another example, another manufacturer. And they use line drawing, but they show you their ventilator. Again, they show you the tubing circuit, and they show you an analyzer and a test lung. What they fail to do here is give you any guidance on which ports on the analyzer to use. Okay. So of course, there's going to be additional information in the manual that tells you things, but just from this drawing, you really can't tell. Third example. And this is a great one. It just simply says, hey, tee in a calibrated test device, a flow or volume analyzer, and then make sure that it's able to display VTI. And it leaves it completely up to you on how to set that all up. Okay. So it's going to be very important for everyone to understand how their analyzer works. There's several out there, and we advocate for certain ones because we've been in the industry for a while. But the most important thing is that everybody understands what they all have in common and how each one is applied to these different test setups. So let's look for some opportunities. Okay. Again, first thing to do, really understand your analyzer. Like most things, analyzers probably have more features than you typically use. But the more you know about the features and the capabilities of your analyzers, the easier it will be for you to do testing. Depending upon the analyzer that you use, you can have very different setups and still measure the same parameters. Case in point, our first photo that we had here, right? It's a photo with an analyzer. It looks fairly straightforward, fairly complex actually. Okay, and so if we substitute a different analyzer, we might have a much simpler setup. Still can measure all the same things, just with a different analyzer. Okay, either way, you need to know what your analyzer is capable of and what are all the components of the analyzer. Some have a lot of components, some have very few. So other opportunities. We want to select gas flow analyzers that allow simple setups. I know you can't just go out and trade in your analyzer. We'd like you to do that if you could. Come to our booth later if you have that in mind. Wait, I'm not supposed to sell anything here. But if you can, look for an all-in-one device, something that does allow simple setups. Things like a device that lets you connect a patient circuit to one side and a test lung on the other, and then it does all the measuring for you. You don't have to tee anything in, you don't have to add an oxygen sensor, you don't have to do anything. You just connect the patient tubing circuit, the test lung, and take the measurements. So having a simple setup really helps reduce the number of errors that you might make. In addition to that, it also does something, it makes you more efficient, right? And if you're more efficient, it saves you time. And what's time? Money, absolutely. So investing in a good analyzer, eventually over time, could save you lots of money. Any questions so far?
Yeah, we have an analyzer that has high flow, low flow modules.
Yes?
What's considered high flow, low flow?
If you look at the module, it will tell you, okay? But typically, high flows are above, what, 50 liters per minute, Nate?
Yeah, 10, 15, 20
10,
in that
15.
range usually.
Yeah, somewhere in there. And low flows somewhere down below that. So, yeah, there's a lot of different ports on a lot of different analyzers. Some have different whole modules to do things like that. Okay. The next thing that we do, or that we want to talk about, is a challenge that we face all the time, and that's ensuring that whatever gas flow analyzer we're using, that it's set up correctly. There's a lot of kind of science to follow, and we won't get too far into it. But we're going to talk about gas type. We're going to talk about gas standards. We're going to talk a little bit how those are used to do volume and flow measurements. We're going to talk about trigger settings. Trigger settings are used anytime that you want to do a breath-based parameter, things like PEEP, rate, tidal volumes, things like that. And the fourth thing that we want to talk about with regard to settings is the measurement parameters themselves. Analyzers have a lot of different settings on them. Ventilators have a whole bunch of different settings on them. Sometimes they call the same thing by a different name. For example, you might have an analyzer that says breath rate on it, or just rate. And the ventilator you're testing may say frequency. And it means the same thing. It's still how many breaths per minute you're delivering. Same way with maybe peak inspiratory pressure. People familiar with that term? Right? Sometimes we call it PIP, sometimes it's called things like that. On an analyzer, you might see it called P peak. Different name, same measurement. Okay, so knowing all those measurements and then making sure that you're also using the correct unit of measure for each of those measurements, all very important. Okay, some ventilators, and we're, here in the US, we usually use mostly like centimeters of water for pressure, liters per minute, or maybe milliliters per minute for flow. But it's important that you're using the correct unit of measure as well as the correct measurement setting. Any questions so far? Okay, let's dive a little deeper into our gas type and gas standards. Okay. Now, gases have characteristics, right? Right now, we're breathing a mix of gas, mostly nitrogen, and some of it oxygen. Does anybody know what percentage of oxygen we're breathing right now?
21.
Around 21, sometimes called 20.8, right? So that mix of nitrogen, oxygen, and a few trace gases, what do we call that? Air, right? Sometimes room air. But for measuring air, we know that there's always some oxygen in it. In the medical industry, we can add oxygen, change the actual characteristic of the gas that we're trying to measure. Okay. In some rare cases, you might have things like heliox and some other exotic gases as well. But I think for most people, most of the time, you're measuring air and oxygen in some combination, whether it's just air at 21% or all the way up to 100% oxygen. But gases have different characters. What's the word I'm searching for? Characteristics. Thank you. And let's say we take a known amount of air, we put it in a container, and we call that a volume of 0. Okay. So depending upon what the characteristics of that gas are, we'll have X number of molecules in there, right? Then if we take that container and we increase its temperature, what's going to happen to that volume in the container? It's going to expand, it's going to grow, right? It's going to get bigger. All right. If we add more water vapor, what happens to the volume? Also expands, maybe not to the same degree as it did with temperature, but it will expand. This expansion can be measured, and so we know that given a known gas and a known temperature, we know that the volume is going to be changing by a known amount. Same for water vapor. If we pressurize that gas, what happens to the volume? It decreases. What happens to the temperature when we compress gas? It increases, right? So they're all interconnected. All right. If we change the character of the gas, if we put more oxygen than nitrogen in there, it also increases the volume. So this is a lot of information about the condition and the characteristics. I don't know why I keep stumbling over that word. The characteristics of the gas that affect its volume. And if we want to measure flow, we need to know all of these things. Okay, so our analyzer is going to take that information. It's going to take the fact that the same number of gas molecules are going to occupy a different space based on the condition of the gas, and it's going to calculate things like flows and volumes. So what we have to do is we have to tell our analyzer what the gas characteristics are. But we don't go and say, oh, well, I know the gas density or the gas viscosity or its viscosity coefficient. We just say it's air, okay? Or we say it's oxygen, or we say it's a combination. And the analyzer then knows that that's the gas type we're using. So we want to make sure that whatever gas we're measuring, we tell the analyzer what it is, okay? And you'll see that there are some automatic settings where the gas analyzer uses its O2 sensor to tell you, okay? So there are some that have automatic settings for oxygen. The rest of these are things like pressure difference over the flow channel. Inside some analyzers that use a differential pressure to calculate flow, there will actually be a pressure drop, a small one inside the channel. You can measure gas pressure, you can measure gas temperature, humidity, and oxygen concentration. Those are all done by the analyzer itself. And together with the gas type, it will calculate flow rates. And what's flow over time? Volume, right? So we call this gas flow measurement. A lot of information goes into that. You're lucky that you have a gas flow analyzer. You don't have to calculate all those things. It does it for you. All you have to do is make sure you match the gas type and the gas standard to whatever you want to measure. We'll talk about that more. Questions so far?
How critical is to replace that O2 sensor on the gas flow analyzer? I know it has like an expiration date, but does it vary a lot if it expires?
Yeah, it's more important that you calibrate it, and if it fails calibration, replace it. The typical analyzer that's has a galvanic O2 sensor. Normally, those are good for about 2 years, depending upon how much oxygen they've been exposed to. But it's important that you calibrate it, and that if it is expired, that you replace it, because it can change, right? If you set your analyzer to air and O2 auto, for example, where it uses the O2 sensor to tell you how much oxygen's in there instead of you telling it, now your gas type might not be accurate. So anytime that you have a gas type or a gas standard that isn't accurate or that isn't correct, then you're going to start getting measurement errors. Okay? Question?
Is there a calculation, so you have set for oxygen, you're measuring,
Yes.
is there a calculation difference, like a percentage
Yes, because they both have different gas densities, right? So if you're just using air, it's already 21% oxygen, but if you switched over to 100% oxygen, now you've changed the gas density. So you need to tell your analyzer, I'm measuring 100% oxygen, or let its sensor tell you what it's measuring. You have two choices.
But if you were had it set to 100%, you're measuring air only.
Yes.
Is there a calculation to figure out how long you're measuring?
There is,
Mhm.
yes. I mean, off the top of my head, I don't know it, right? What percentage it is, but yes, there is a calculation that tells you, yeah, you're off by X number because you're measuring the wrong gas. Yeah, it's fairly significant. Things like temperature are more significant. So all these different things, these conditions of this gas that we talk about, along with its characteristics, some influence more than others, how much volume changes, okay? All right, where were we? So we have a process that we call gas flow measurement, taking all this information into account. Normally our gas flow, when it's going through a device, it's being measured by a flow sensor. We're actually measuring what the gas temperature and pressure and saturation is at that time that we're measuring it. And that's a gas standard called ATP, actual temperature and pressure. So sensors measure in that gas standard all the time, okay? Now, it may be necessary or convenient for us to convert that measurement to a different gas standard. Has anybody else heard of other gas standards besides ATP? Anybody heard things like AP21, BTPS, STP? There's about 17 or so recognized gas standards out there. So you might have to do a conversion, or your analyzer might have to do a conversion so that you can compare apples to apples, right? Let's talk a little bit more about that. But be aware that we may measure the gas very accurately at ATP and display it as another gas standard. That's the biggest takeaway from this one, okay? So let's see a real life situation, what happens, right? Here we have a ventilator. We've got a patient circuit. We've got it hooked up to a patient. We have a return circuit from the patient. On the way to the patient, gas comes out of the ventilator. And let's say that it's set at 500 mils, tidal volume, okay? As that tidal volume goes through the humidifier and past the heated limb of the circuit, what happens to its volume? It's going to increase, right? You've increased temperature, you've increased humidity, you've increased volume, okay? So now what the patient is actually getting is a volume that's actually more than 10% higher than what the ventilator is delivering, okay? In the old days, ventilator operators, therapists, they had to do that calculation themselves, okay? They had to look at their patient and say, oh, I want to deliver, 500 mils to them, then they wouldn't punch in 500 mils, they punch in something lower, right? In this case, if they want to deliver the 560 to their patient on this particular ventilator, it's going to display in BTPS. Okay, so its display will tell them what is going to happen to the gas by the time it gets to the patient, not what it's actually being delivered from the outlet of the ventilator. Does that make sense? Okay, so many ICU ventilators do use BTPS as a gas standard. That makes it convenient for the operator so that they don't overinflate their patient's lungs. Patient safety, right? Number one for all of us. Okay, well, how does that affect us? When we test a ventilator, what do you use to test it with? Is there a humidifier in line? Are you humidifying the gas? Or are you just simply connecting your ventilator to your analyzer, right? So here, again, if our ventilator is displaying BTPS, let's say we've typed in 560 as a setting, and the ventilator's spirometry is telling us, yep, you're giving 560 out. Well, in reality, when it gets to our analyzer, it's not really 560, right? It's going to be about 500. So this looks like there's something wrong here. One of these devices is not measuring correctly, right? I'm off by more than 10%, and this is just at one point. What happens if I test over a big range of volumes, right? I'm off by quite a bit here. What's the problem? Do you start troubleshooting now? Do you say the ventilator's no good? Do you say your analyzer needs calibration? What do you do? Try a different analyzer, right? Chances are you're going to get the exact same results though, right? So if we look at this and we say, all right, the ventilator's saying that it's delivering 560. We know that its output is really 500 because we converted ATP to BTPS on the ventilator display, right? There's no change in the gas as it goes down the patient circuit. It doesn't get warmer, it doesn't get more humid, so its tidal volume doesn't increase. So when it gets to our analyzer, we're measuring 500. We're actually measuring what the ventilator is putting out, even though the ventilator is saying it's more than that. Again, that's that convenience conversion for the operator. So what can we do? We can take our measured value from our device and say, all right, there's a big error here because of these mismatch between gas standards, right? So if we set our analyzer to BTPS, it's the same as the ventilator, and now both of them are going to display the same volume, even though they're both actually measuring less. Does that make sense? So again, the big takeaway here is make sure that your analyzer is set to the same gas standard as the unit under test. It's not always easy to tell what the units are being displayed on a ventilator. Sometimes you have to dig a little deep. You have to go to the ops manual and say, hey, this is a curtain bed at 840. What does it display in? Is it ATP, STP, one of the other 17 gas standards, or is it BTPS? And then you set your analyzer correctly. And now when your analyzer is saying, or the ventilator is saying 560, but it's putting out 500, you're measuring the 500, but it's displaying 560. Now you have apples to apples and you're happy. Okay, in this case, it might be bananas. No. Question. Not always. No. Like I said, sometimes you have to dig for it. You have to go look at the ops manual, look at the service manual, call the manufacturer.
Yeah, really.
You know,
yeah.
Sometimes it's that bad, right? Okay.
What is ATP?
Actual temperature and pressure.
Okay.
All right. So that's what we're really measuring,
Okay.
right? Because the flow sensor doesn't care, right? It can be warm, it can be dry, it can be wet, it can be cold. It doesn't matter. It's going to measure the actual flow.
Okay.
Okay. It's just this convenience factor that was been built into ventilators that give us all these other different gas standards. Okay. Again, match your gas type, match your gas standard, you're good to go.
Okay.
All right. I'm going to hand off. I'm going to quit talking, let you listen to Daniel for just a minute. He's going to tell you about some more of the question before we move on.
Is there a way we can have access to those slides that way we can have the notes instead of taking pictures?
I think they're recording.
I think they're
this, right?
recording this, so
Yeah.
you should be able to see
Yeah.
the whole thing.
Yep.
Oh, perfect.
Yeah.
Absolutely.
Okay. Take it away, Daniel.
Yeah, thank you, Kerwin. That was a great explanation. Again, just one of the key takeaways is really make sure that your gas standard matches the device on the test. That's really, if there's one thing that you need to remember from today, then I would say it's that one. That's so important. And because gas flow analyzers measure all these parameters, they can convert to any gas standard you would ever see on any of the ventilators you're testing. Again, most frequent use ones are BTPS and maybe STP. So these two you'll see most often. All right, good. So next settings we want to talk about. You see, we spend a lot of time on this second challenge with the settings because it's the most important one in our opinion. The next one is called trigger settings. Have you heard about that? What that is? Trigger settings? Anyone? So trigger settings, so we talked about gas type and gas standard. These are important to really measure the flow rate, and flow over time is volume, right? But gas flow analyzers can measure a lot of additional parameters and things you will see on the display. Yeah, question?
Like when it's triggered, is that when the patient like breathes?
No.
And then triggers it?
But we'll talk about that in just a bit. Yeah, that's a very good question. I'll talk about that in just a second. So trigger settings are also used on the ventilators, but trigger settings of a gas flow analyzer are used for the gas flow analyzer to identify the breath phases of actually the ventilation that is going on through the gas flow analyzer. So we have typical flow waveforms and pressure waveforms here. So the gas flow analyzer needs to know what is an inspiratory phase and what is an exhalation phase. And the reason why it needs to know that is to calculate the so-called breath-based parameters. Things like Kerwin already mentioned, tidal volumes. So how much volume has flown to the patient in the inspiratory time and how much volume came back from the patient or the test lung in our test setup through the gas flow analyzer. Or things like a respiratory rate or the I to E ratio, which is what is the ratio between inspiratory time and expiratory time, or the PEEP value Kerwin talked about earlier as well. These are all, and there are many more, these are also called breath-based parameters. And if the ventilator tester, the analyzer, can't tell what is an inspiratory and an expiratory phase, it's not going to be able to calculate and measure all these values. Does that make sense so far? So whenever your device is not, we say, triggering, then you would just see dashes for these values maybe on your display, or something that's saying like no trick, say no trigger. And gas flow analyzers typically also have a trigger indicator. So for example, our ones, they have some small T that is flashing up on the display each time when the device is triggering. So if you see that your analyzer is not triggering, that means your trigger settings are off. And we talk about two triggers. One is called the start trigger. That one we will set in a way that we can detect when an inspiratory phase starts. And then there is also an end trigger, or sometimes they call it stop trigger. That's actually when the inspiratory phase ends. And that means at the same time when it switches to exhalation, right? So everything between our start and end trigger is inspiration, and everything between the end and the next start trigger is exhalation. And with that, the analyzer can then calculate all kind of stuff. So again, this is not to be confused with trigger settings on ventilators. Trigger settings on ventilators are used to set the sensitivity of a ventilator for spontaneous breathing by the patient. So for example, you can say if it detects a negative flow when the patient wants to inhale of, let's say, 3 liters per minute or 5 liters per minute, then that means, oh, the patient wants to take a breath. But that has nothing in common with that. Some people think that this is related, but it's not at all. It's just the same terminology. All right, so another thing we need to make sure, and I think that makes sense, we need to make sure that our trigger settings are as close as possible to the real breath cycles of our ventilation ongoing. So this is going to be one of the challenges we're going to talk about. Because if we are not close to the reality, then our calculated values will be wrong. Here we have an example of inspiratory tidal volume. So this is an inspiration phase, so this is the flow over time, and mathematically what the ventilator tester, the analyzer, is going to do is going to integrate the flow over time from the start trigger to the stop trigger, and then say, okay, this is actually the shaded part here under the curve. Mathematically, this is going to be my tidal volume, my inspiratory tidal volume. And in this example, you can see here our triggers are a little bit too late. So the inspiratory phase starts here, but our trigger is a little bit shifted. The same applies for the end trigger here. It's also a bit delayed. And what happens here is we're going to miss in the calculation this first part of the volume here. But even worse, it's going to take a bit of the exhalation phase and also consider this as inspiration tidal volume. And because the flow in this example goes negative here, this is going to be considered negative, so it's going to be deducted from the calculated volume. So in examples like this, we will have a tidal volume which is not really accurate anymore because our trigger settings are not accurate. Does that make sense so far? Yeah, question?
Now, you can't set this up in your analyzer.
You can.
You can?
Yep.
Okay.
That's exactly what we're going to talk about right now. Yep. So the question, yeah, before we talk about how we find the best trigger settings in a specific application, let's talk about some basics. So trigger settings are always defined as 3 main parameters. The first one is a trigger source. So there are different sources we can use for triggering typically with gas flow analyzer. It could be just a flow channel of the analyzer. It could be a pressure port as well, or it could also be a digital signal that is created or generated by the ventilator, and you connect a digital cable actually to the analyzer, and this triggers the breath cycles. Then the second parameter is a trigger signal. So typically you can select between a pressure curve to be watched for the trigger or a flow waveform. And the third parameter we will talk about is the trigger level. So this specifies the threshold when the trigger should be activated. And beside the value itself, we also need to tell the analyzer then, should it trigger when this threshold is reached in a rising edge of the signal of the waveform or a falling edge? That sounds very complicated, right? Let's go through some examples. So the main challenge is actually to find a good trigger signal where we can set our trigger levels as accurate as possible to the reality, to the breath transitions. So let's have a look at some example signals and judge how good they are qualified for trigger signals. So this is the first one. So this is a flow signal, as you can see. And these dashed lines here, these gray dashed lines here, indicate the real breath phase transition. So the first line is actually the start of an inspiration, and the second line is the end of an inspiration phase. And the gray area here around the 0 line is actually an area where we don't want to have our trigger levels because a little bit of signal noise could then cause false triggering. So who thinks that this is a good trigger signal? Raise your hand. Don't really know, not sure? Okay, let's have a look at it together. So we want to set our triggers for our analyzer using this signal as at the start of an inspiratory phase and the stop of an inspiratory phase, right? At the end of an inspiratory phase. So let's have a look at it. So because here the start trigger is pretty good because this signal rises very rapidly. We talk about a steep slope of the waveform. And because of that, we can then set a trigger level here, this dashed line, right a little bit above our gray area where we want to avoid triggers levels to be because we risk false triggering. And that gives us a very accurate indication here when the inspiratory phase starts. However, the problem here with this signal is at the end of the inspiratory phase, you see the signal is very flat and the changes are marginal within that gray area we don't want to be. So it's very hard to set a trigger setting here when the inspiratory phase is over. Do you all agree on that? If we would set it to the same level, but on a falling edge here as our start trigger, then we could trigger, but then our inspiratory phase that the analyzer detects is way shorter than the real inspiratory phase. And that's going to affect all our measurements of breath-based parameters. So let's have a look at the second example. How about this one? Looks a little bit better, right? Because here we have a positive flow through the flow channel in the inspiratory phase and then a negative flow during the exhalation phase. And at both real breath transitions, we have some kind of movement in our signal, which is good. And we can set our trigger settings on that. So here we could set the start trigger to a positive flow on a rising edge, and then the stop trigger or end trigger at a negative flow on a falling edge. And that would allow us to quite accurately capture the inspiratory and expiratory phase. However, you see in this example, the curve or the waveform is not that steep as in our first example. So that again means that we are missing a little bit of timing here, and it adds a little bit of more inspiratory time at the end. So for all our timing-based parameters like a rate or an inspiratory time, this is not going to have a big impact because the actual length is still the same. It's just a bit shifted in time. But again, here for the volume calculations, we are going to miss a little bit of volume here, and we're going to count a little bit of volume negative over there. So this is a good trigger signal, but still not ideal. So let's have a look at the last example. How about this one? What do you think? Good? Yeah, this one is perfect, because here we have very steep slopes of our signal at both breath phase transitions. So we can set a start trigger here very accurately and an end trigger here. So that allows us to trigger perfectly in sync with the reality. So this is really good. And the lesson we have learned here is a good trigger signal has steep falling or rising edges or slopes at the transition of each breath phase, inspiratory to expiratory phase and back to inspiratory phase. Any questions so far? I know this sounds challenging. The good news is that most gas flow analyzers have default trigger settings. Most of the times you can see default trigger settings for adult ventilation, pediatric, and high frequency. And these default trigger settings work well in most applications you will ever see. And the reason is because in most applications you will have your gas flow analyzer, ventilator on one side and test lung on the other side. And then you will have a positive and a negative flow through the gas flow analyzer. And no matter if you are, usually you have either you are in pressure controlled ventilation, maybe you've heard that term, or in volume controlled ventilation on a ventilator. And in both these cases, we can see typical waveforms here is pressure controlled and volume controlled. And most important is in both cases, we have flow signals that have very steep rising and falling edges. So we can easily use the flow signal as a trigger signal for most of our applications. And another thing that is nice here is it all happens around the zero line. So no matter what pressure we have set up on the ventilator or what volume, usually it just starts at zero flow and then it rises up. And in an inspiratory phase and in an exhalation phase, it transitions to negative flow through the analyzer, and then it comes back to zero. So that means our trigger settings are not dependent on the settings on the ventilator. Yeah.
Are these do you make settings in the analyzer to get a steeper?
No, the signal is how it is. You need to find the settings that match this specific application.
Okay.
Yeah, but again, because this is the case here in most or in all the analyzers we've seen out there in the field already, their default trigger settings are, as you can see on this slide, or very close to that. Maybe it is not 3 liters per minute, maybe it's 2 liters per minute, but that doesn't really matter. But the thing is, they all have default trigger settings with using the flow curve and a start trigger on a rising edge on a, let's say, 2 or 3 liters per minute of flow, and a stop trigger on a falling edge of negative that flow, 2 or 3 liters per minute. And that works well in almost all the applications where we have a positive and a negative flow through the flow channel. However, sometimes, eventually it happens that this is not sufficient for your application. Let's have a look at such kind of an example. So here we have a setup for a so-called BiPAP ventilation. Is anyone familiar with BiPAP? Okay, BiPAP means the ventilator is applying 2 different pressure levels to here the test lung. And in this setup, we have a defined leakage in front of our test lung. So this is to simulate a typical non-invasive patient interface with a mask, for example, that has a defined leak. So in this application here, when the ventilator applies the higher pressure level, there's going to be flow through our gas flow analyzer, volume filling up our test lung, and then when it releases the pressure, the volume is actually leaving this leakage here and not flowing back to through our analyzer. So that means, remember, our default trigger settings that we talked about earlier, they're no longer going to work because we don't have any negative flow. Never we have negative flow through our gas flow analyzer. So in this situation, our pressure and flow curve look, for example, like this. And as you can see, our flow waveform here is not sufficient for triggering due to the lack of a steep rising or falling edge at the end of the inspiration phase. On the other hand, the pressure signal looks good here, right? We have steep edges, so we can use the pressure signal. As we have learned earlier, we can select in the gas flow analysis, do we want to use flow or pressure signal to trigger. So in this case, we could trigger on the pressure signal. The upper pressure level in BiPAP is called IPAP, and the lower level is called EPAP. So in such a situation, we would typically set trigger settings, the start trigger on a rising edge on EPAP plus 1 centimeter of water pressure, and then the stop trigger on a falling edge at IPAP minus 1 centimeters of water pressure. So that allows us to trigger in this specific application here. But the challenge now here is that these trigger levels are dependent on the settings of my ventilator. Because let's assume that my first settings that I have to test is an IPAP of 6 and an EPAP of 2. So I would then set my trigger, start trigger to, let's say, 3 centimeters of water pressure and my stop trigger to 5. And let's assume that my next setting on my ventilator is going to be IPAP of 8 and EPAP of 4. As soon as I apply these settings, my gas flow analyzer is going to go, whoop, not going to measure any breath-based parameters anymore. Why is that? Yeah, it's not triggering anymore, right? If we have a look at the updated graphics here, our trigger level, our start trigger level was at 3, and now our pressure is never going to go below 4 anymore because we have the setting now on a higher levels, right? So to resolve this, we'll have to amend our trigger settings to the new settings on the ventilator so that the device can trigger again and measure the breath-based parameters. So as you can see, in some applications, it's absolutely critical to understand how trigger settings work and how you can find the suitable trigger settings for your specific application. Any questions so far? All right, there are 2 more trigger settings that you will come across. They are not used very often. I just want to cover them a little quick. You will see a term called trigger delay. A trigger delay can be used if we have like signal noise or spikes that are above the trigger level, and we want to make sure that the device is not triggering because of that. So we can define how long a trigger condition needs to be true until it's actually considered as a real trigger. So if it's a spike only that resets the trigger condition in just a couple of milliseconds, then it's ignoring that trigger. The other thing that you will come across is called base flow. A base flow is needed if you have an application where you have an offset of flow of a ventilator that is compensating a leak. And if you want to, for your tidal volumes, this is going to bring it out of balance. So we'll have far higher tidal VTIs and far lower VTEs because of that constant offset of flow. So we can tell the analyzer that offset, and then it's not going to consider that in the volume calculations. But again, this is a little bit more advanced, and in most applications, you will not need to have to change settings like that on your gas flow analyzer. Okay, the last thing on the settings side, so we talked about gas type, gas standard with Kerwin, and now trigger settings. And the last thing Kerwin mentioned in his introduction, and I'm not going to talk more about it because you explained it very well, we need to make sure that we are looking at the right values on our gas flow analyzer, right? And that we have it set up in the same unit of measurement as on your ventilator. So you're comparing apples with apples or banana with banana. So yeah, again, there are different terminologies. Sometimes the ventilator manufacturer calls something different than your analyzer, so you need to know that and make sure that you look at the right value. So what are the opportunities imposed by all these settings changes that we talked about? So one thing, if you have a gas flow analyzer that features profiles, then it's highly recommended to use profiles. So modern gas flow analyzers let you save all your settings in profiles, so you can load them later on if you have come across the same application again. So profiles hold settings like gas type, gas standard, your trigger settings, and all your measurement screen customizations you have made on your gas flow analyzer. So that's very convenient because sometimes it takes some time to figure out, okay, what are my right trigger settings? I figure out by calling the ventilator manufacturer what gas standard it is using. So I want to make sure that I save that for later on, right? And most modern gas flow analyzers offer this feature that you can save all that as profile and then name it somehow, and then you can load that later on. And this helps minimizing the risk of setup-based, settings-based errors and reading errors. Some gas flow analyzers even allow you to kind of group the measurements and color them differently, which is really nice sometimes. So, for example, if you have all your pressures in red, then it makes it easier for you to allocate the value you want to look at more reliably. The second opportunity here is to use some advanced aids and automation features that your gas flow analyzer may offer. So watch out for things like on-device waveform analysis, because when you want to find a suitable trigger signal and trigger levels, then it's very nice if you can measure on the device and you can see the waveforms. Okay, I have a steep slope here. Oh, my trigger level is best set here and there. So that helps a lot if you're trying to figure out suitable settings here. And there are also features like graphical trigger indications, for example, as you can see in these pictures, that gives you guidance. Okay, what are the impacts of my settings on my waveforms? Where am I triggering, on which waveform, and on what slope of the signal? And the latest gas flow analyzer generation even features automatic trigger detection. So these devices are able to analyze the flow and pressure waveform in real time and then find suitable trigger settings for you automatically. So just imagine how helpful that is in a situation we discussed earlier when you have triggers levels that are dependent on the setting of your ventilator. So with such an analyzer, it's just doing that automatically for you. All right, so this helps to find most accurate trigger settings for most accurate breath-based parameter measurements. All right, so we'll jump into the last challenge. Have you ever faced challenges that we discussed so far, the ones that are working on ventilators? Raise your hand. Okay.
Just a general question on your parameters. The 980s, they've got humidifier, non-humidifier, but you go in there and use it. Are you using a humidifier to set up your therapy for that? And in the classes, when you do your testing.
Yep, that's a good question. Yeah.
So is that what you're talking about with your parameters and your standards?
Yes.
Yes.
Correct. Correct. The ventilators like that sometimes also, there are also ventilators, as soon as you go into service mode, they change the gas standard because they know, okay, then typically you don't have a humidifier in line. But some ventilators have really a button, and then they would change typically between BTPS and something else, maybe STP. But again, what Kerwin mentioned, you need to know that what your ventilator actually is using to display in any case, right? What effect that button exactly has is hard to tell. I don't know it by heart with PB 980.
The 980?
Yeah. Is it BTPS and switches to what? STP
ATP
maybe?
or STP.
ATP or STP, yeah. Yeah. That's usually that's mentioned in the service manual somewhere. Yeah.
So they saw the problem that we talked about, people not knowing what the ventilator's delivering, and they're measuring it with an analyzer that's measuring ATP. And they're getting a lot of complaints saying, hey, your ventilator's off by over 10% on every measurement. And they go, oh, well, push this button and that solves the problem for you.
Yeah.
So it's a different workaround.
Yep. All right. Thank you. Okay, so we just have 5 minutes left. The last challenge we're gonna go through quickly is sometimes we see that the sequence and valid ranges defined by the ventilator manufacturers quite challenging to understand and to follow. So we have two examples for you. It's not expected that you can read everything here, but this is an example where we have to, very typical application where we have to calibrate different pressure levels. And sometimes it's as easy as it says, okay, set the pressure to 10 on the ventilator and your analyzer should read 9.5 to 10.5 or something like that. In this case, it's very complicated. So you have to go through a lot of calculation. They even added an example in the appendix, so to make it easier for you, or trying to make it easier, because you have to first read the value on the ventilator. So we detailed it a little bit for you. It's 9 steps per pressure scale point. So you need to read the value on your analyzer and your ventilator, then you need to calculate an average, then you need to, based on these measurements, plus minus 15% is going to be your upper and lower limit. So you need to calculate that yourself. And then finally, you can judge whether your calculated value is within the calculated range, right? So of course, it's important that you get trained on these ventilators, but procedures like these are very cumbersome and very prone to errors, right? There's another example here. It's about a flow calibration. Here, even they say, oh, if your flow is fluctuating, you have to kind of build a median value yourself in your head. So, oh, it fluctuates. It's 100, 101, 196. So it's probably the average is about 99. And then again, you need to take that value, calculate your upper and lower limit, and then finally judge your measurement if it is a pass or fail. So again, multiple manual steps that pose risks of misinterpretation, miscalculation, right? So the last opportunity I want to talk about here is actually a feature that the latest gas flow analyzers on the market offer that actually not only resolves this challenge, but all the challenges we discussed so far. And it's to use guided testing apps or test sequence features. So these gas flow analyzers have built-in testing applications for specific ventilators. So what they do is actually they guide you through the performance verification of that specific ventilator. So they show you how to set up the test setup with your device that you're using. They take the measurements automatically. They calculate the valid ranges based on the measurement, and they can give you pass-fail results right there on the screen, because it's all known, because we program the service manual procedure is actually programmed into an application running on the device. And the nice thing is also it saves all these measurements and can then create a test report for you with all the results. So this helps, of course, to make your testing more efficient, and also eliminates the risk of measurement and transcription errors, and also setup errors, because it shows you how to set it up. And additionally, when you start this application, this testing application, it knows what gas standard is being used by this ventilator, it knows the suitable trigger settings, and sets that up for you automatically in the correct manner. So yeah, that was it actually, what we wanted to discuss with you. I'll hand it back to Kerwin for a little summary of our key takeaways.
Yeah, we'll do this really fast. We need to get you out for lunch.
Yep.
Again, ensure that you understand the features and capabilities of your analyzer, no matter what it is, okay? Quick question for you. Who has an analyzer now and they're using it on a normal basis, okay? How many times have you looked at waveforms on that analyzer? You will look at waveforms sometimes? The actual waveforms, not just the numbers. Because a lot of people look at just the numbers, right? But you look at waveforms too? That's good, right? Know that those tools are in that device, okay? Analyzers are like a multi-tool, right? Like the old Leathermans or Gerbers, or, you know, the original multi-tool, the Swiss Army knife. Lots of cool tools in there, but you need to know what they're used for, okay? Pay special attention to your setup, as we said before. Make sure you're setting up properly, making sure that all the settings are correct, that we keep harping on, gas standard, gas type. Something to do before you start measuring is warm up your device when you're setting it up. Okay, let it warm up, zero it out, get it ready to go, and then make sure your gas standards and gas types are correct, and then start your testing. Okay, make sure it's set for the specifics that you're trying to measure. And last of all, take advantage of the features that we're talking about here. A lot of people don't take the time to learn their device. They go to class and they say, okay, your volume number has to match this volume number, your pressure number has to match that one, your PEEP matches, the O2 percentages, those have to match. You do multiple settings on the device under test and you take multiple readings and you're done. But if you take a little bit of time and look at these advanced features, they'll help teach you what you're actually measuring, okay? I know it takes a lot of time and you're very busy, but in the long run, it will save a lot of headache. It will increase your accuracy. It will increase your efficiency. Okay, we are at booth
305.
305. If you want to talk more about this, come see us during the exhibit hours. And you can take a look at our analyzers. You can compare them to ones you may have used before. If you're using ours, thank you. We like that. If you want to know more about them, or if you want to talk about features of the analyzer, we're happy to share that information with you. Thank you very much. Any
Yeah, thank you.
questions?